general public forecasts that you can see on the radios, televisions, and so on. Okay, so let's start with the first slide. And this is quite interesting because in science or in other activities, we have these old chaps that are prophets or are visionaries, and this guy, Richardson, was a guy that was a polymath, I would say. So he had a degree in physics. He also was a mathematician. He also was a psychologist. But interesting, during the First World War, he was he joined basically this ambulance unit, and during the spare time he was looking how to make a forecast. So he made some first computations to make a weather forecast, unsuccessfully at that time. But this picture that you see in this slide, it tries to summarize his vision, what could be in the future a weather prediction. So you see here this kind of a big stadium with thousands of people. He computed, he guessed that at least more than 50K people were able to involve in this enterprise. And on the top, you see this dome where you project this map, this globe on the dome, where you can see Africa, Europe, North America, and so on. And where we have these thousands of people working together to generate a forecast. So on the dome, if you notice in more detail, these squares that are projected on the dome, and these squares are basically the units where each team of people were dedicated to compute, let's say, the temperature, the wind, speed, the pressure, and so on. And then we had this column in the center of the stadium where a maestro would coordinate all the efforts and pass the information from one grid square to the next grid square. So this was basically the vision of Richardson at that time in 1923. 100 years later, or almost 100 years later, these forecast factories that Louis Richardson proposed are real. So these are two examples. One is the Met Office building that you see on the top, and the other one is where I'm working now, the ECMWF. So both of these are the present forecast factories where the forecasts are generated more than once a day and disseminated to the public and special users. So the dream of Richardson was not so far away from, in fact, what we got it nowadays. Now, just to present a quiz. So what we have here is a kind of an image viewed from a satellite perspective. Imagine a geostationary satellite positioned above the equator, and one of them is a real satellite picture. The other one is produced by a numerical weather prediction. So, and they are basically for the same date. So which one is the real picture? I leave that for the end of the presentation, but you can look at it and see how the details are basically similar in each picture, and it's quite, let's say, interesting to see exactly which one is the real one. Okay, so if I wanted to, let's say, put this in a very short recipe, I would say the numerical weather prediction is basically a combination of the mathematical physics laws. So we have a model. Then we need a global observation system. So without it, it's impossible to make a forecast, because a forecast from a scientific point of view is an initial value problem. So in order to predict the future, we need to know the present conditions. The third point is we need computers. So instead of these 50,000 people working to produce a forecast, as Richardson envisaged 1 century ago, we now have big computers, high performance computers, which can do the work for us. And then finally, because this is a very complex problem in physics, we need to quantify the uncertainty of a forecast, okay? Because it doesn't make sense to make a forecast for tomorrow or the day after saying if it will rain in 2 days' time, yes or no. So this is not the way we should make a forecast. So just in a slide, I don't want to scare people, but just to show that there is real science behind it. So we start with the second law, Newton's law, which basically shows here the c is the wind speed or the wind vector for those which are more familiar with mathematics and physics, and the change. So the term on your left, on the top, so this first equation shows that the change of the wind speed in a very, let's say, simplistic way, it depends, in fact, of other terms, which is the rotation of the Earth, because we are in on a planet that has a rotation itself, and also the second term refers to the buoyancy effects or the gradient pressure effects. So, and an example is when you dive in the ocean, you feel the pressure in your ears. So this is the pressure acting on your body. And then we have the third term, the G, which is basically the gravitational force, which basically pulls any body towards the ground. And then finally, we have a term which is the dissipation. But what I think is important to state here is that this equation is valid for the picture on your right that you see here. So this kind of a cyclone with this cloud band, which has a scale of thousands of kilometers, and is valid as well for the second photo that you see, that is a tornado that is a length scale of 1 or 2 kilometers wide. So the same equation can be applied to describe the winds around the cyclone, or around the tornado, okay? Then we have the conservation of mass, which also we need it because the mass, so the atmosphere is a fluid, so the mass basically is important because it has to be conserved. So we cannot destroy mass. We don't see the atmosphere to move away from the planet Earth for the time being. So, and then an example of that, of this conservation of mass, is what we see in the reservoir inductions, so when the inflow basically is an excess of the outflow, so we see the water level going up in the reservoir. If the outflow basically exceeds the inflow, we see the water level going down. So basically this principle of conservation of mass applies to the atmosphere as well. And then we have the thermodynamics, the first law of thermodynamics, which is basically behind the principle of conservation of energy, okay? We have a lot of energy going through the atmosphere, going to the oceans, going back, bouncing back from the clouds. So there is a lot of heat transfer between these different components of the planet Earth, and it's important for us to account for. But unfortunately, we don't have let's say, a general solution for this set of equations. So we have a problem there, which is not having an analytical, as we put in science, an analytical solution for that. And instead of this, we have to find techniques, so numeric analysis techniques and powerful computers to do the job for us, a kind of a plan B, since we don't have the mathematical solution for this set of equations. Now, what those equations and what these numerical models will try to characterize is summarizing this plot. So you have here condensated many processes that are going on in the atmosphere. You know, you have the radiation, which is given by these orange arrows here, that is coming from the sun. So the sun is the main source of energy, and then they bounce back if they are reflected by the cloud, as you can see here, or you have the cloud, you know, producing precipitation, as you can see by these drops, or you have, let's say, the winds acting over the oceans, producing the waves, or you have, you know, the heat coming from the sea into the atmosphere. So there is a lot of processes going on, and those equations that I tried to that I showed before are able to resolve this this phenomena. Now, what is important here is we have the mathematical physics laws that can deal with all this process. But because we need, in order to know the future, we need to know the present, we need, in fact, a very big infrastructure, which is observing the weather, okay? And this is a global effort. So we have, we started in the 19th century with this International Meteorological Organization, and almost 1 century later, we had this World Meteorological Organization, like the World Health Organization, which is now responsible to manage this pandemic that we have now. So these supranational organizations, they basically provide leadership and expertise to promote international cooperation, you know, because this is very expensive enterprise. So we need that most of the countries will share the burden of keeping these observations and measuring the atmosphere, because it's a very expensive to do it just for a single country. So this cartoon here tries to illustrate the complexity of having these observation systems measuring the atmosphere almost instantaneously, okay? And you can see on the top these satellites, so these very expensive instruments, which are basically very high altitudes, measuring very large portions of the globe in terms of radiance. But also we have other types of observation, you know, observations measured by the aircraft or the ocean buoys that you can see in this orange icon here, or ships as well. On the land side, so if you go to the land side, you have on the far right the weather radar, which can give you, you know, for several hundreds of kilometers, a snapshot of the places where we see raining, and or some more localized weather stations, the typical weather stations, like the instrument we have in the Dutch Sailing Club, you know, measuring the winds and the temperature that is on the top of a pole. So all this has to be sent almost in near real time, so can be collected by the National Weather Service, and this will be ingested in our models, okay? So to give you a snapshot of what we how the observations are distributed on a global scale, you have 4 maps. Each map represents a different type of observation. So on the top left, we have the weather stations that we are familiar to us, you know, the simple one that is in the garden to the one that is an official WMO weather station. So, of course, the ones that are in the garden, they are not recognized as an official observations because to be recognized, you need to follow several requirements, you know, and this is very important because otherwise you will make some errors in the observations which will be difficult for us to disentangle. But just to see that most of these conventional data, like the, uh, the observations measured by these instruments in these specific places, most of them, as you can see, are overland, okay? And there is a nice coverage, as you can see, so on the top left, over the most of the continents, except probably over Africa, especially over deserts where the coverage is not so good as we would like it, okay? But nevertheless, it's a nice coverage, let's say, for North America, South America, and also the Asian European continent. Now, if you go to the buoys, these buoys are drifting with the currents. So there is a nice coverage, let's say, over the Atlantic, as well over the Indian Ocean, especially on the South Hemisphere. But if you look to the, let's say, over the equatorial Pacific, we don't see a lot of observations there. So we have gaps which are 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 important to fill in with other types of observations. And you can see on the bottom left the ones generated by the routings, the ship routings, and you can see these straight lines, which are the ships moving with time and producing observations on a regular time intervals, okay? And this tries to cover some gaps that we saw on the previous plots. This is just this slide just is a kind of an instantaneous, almost an instantaneous plot of the observations over, let's say, 8 hours interval, and you see the coverage for the conventional data, so the SYNOP, the buoys, and so on. And in fact, we are quite happy that the land is well covered by these observations, which is important for us to do the numerical weather prediction. Now, what is not a kind of a supplementary observation system in this global observation monitoring is the aircraft. You know, some aircrafts, they have installed instruments which are fundamental for them to pilot the plane, but also fundamental for the numerical weather prediction. And this is interesting to see the line. So each line basically represents a flight path, and every time that the plane is flying is recording or measuring the winds and the humidity and temperature and reporting back to us these measurements. Now, what is interesting here is, as you know, we are under this pandemic and most of the industrial activities was shut down, and also the aviation industry also was severely affected by this. So this was, as I said, this was a plot basically 1 month ago, so mid of March, and we see the density of plots in this map. And if we compare this density with let's say yesterday or 2 days ago, we see that the number of observations went quite down. So around 60 to 50% down compared with the observations made 1 month ago. Okay, so and this has a real impact, of course, to the forecast that we can produce, because this information is not available anymore, at least with the quantity that we would like, and this has to compensate with other observations, like, for instance, these balloons that we release on specific times of the day. So there is a photo here which shows this balloon which has attached a wired with an instrument at the end. And once is released, is basically doing a profile of the wind and humidity and temperature as it moves to higher altitude. So all of these have to be maintained, and of course they have to send this data almost in near real time in order for us to process this information. Another important observation that we nowadays we rely quite heavily is the polar orbiting, and you see these polar orbiting satellites. So each color represents a different satellite. They cover the full globe, but with periods, let's say, about 90 minutes to 2 hours, but at different times. So basically, as they are moving, they are measuring the atmosphere. Okay, and this is the basically one type of satellite images that we use quite heavily, and you can see that the advantage of these satellites is to cover the regions where we have lack of observations. Remember that the oceans were the most missing conventional data. So most of the conventional data was over the continents. So the satellites, they try to complement that information, that lack of information given by the conventional data, and provide some information over the oceans. The same thing for the geostationary satellites, so the satellites that are fixed above the equator. So, and you can see that these disks that they form, measuring constantly the atmosphere over regions in the globe. So they are another type of satellites, and they are very important because, once again, they don't only cover the land, but also they cover the ocean, which is important for us to know. So, summarizing, in numerical weather prediction, we use quite a lot the term of data simulation. What is the data simulation? So the data simulation is a technique in order to describe the current state of the atmosphere in order for us to make a forecast in the future. So without knowing what are the present conditions of the atmosphere, it's impossible to make a forecast. Okay, so basically the simulation takes into account the model, these equations that I show at the beginning, this huge amount of observation. So per day we use around 50 million observations to produce what we call an analysis, so the initial state of the atmosphere, so where we start to do our forecast in the future. So we use the forecast model, we use lots of observations, then we have a mathematical technique to combine the two, and using the supercomputer we produced, in fact, the initial conditions, and use the model to predict the future of the atmosphere. So it's quite, let's say, when we use the apps that nowadays is quite handful to use it on a mobile phone and to see what is the weather forecast for Dutchess in the next 5 days or so, and we see these nice graphs showing the temperature evolution, the wind speed evolution for the next days. But we have to take into account that there are let's say, some assumptions behind those nice maps. And those assumptions is that instead of having a continuous distribution of the wind field or temperature or pressure, what we have is a discrete, uh, basically discrete variables, so a discrete temperature, which are distributed in a grid. Okay, it's like this grid that you see here in this satellite picture. You see those lines crossing each other. So this is a kind of, it's like a fishing net covering the entire globe, and each intersection of the lines, you have basically the location where you will define the temperature, the wind speed, the wind direction, the precipitation, the pressure, and so on. And these are given by the by the equations that we saw before. Okay, and I put it here two regions, one in red and the other in green, just to illustrate two different phenomena that the model can resolve explicitly and cannot resolve explicitly, and has to somehow find ways to take into account those small scale structures. So if you look to the cloud that is inside of this red circle, we see this kind of a frontal system. So it's a very widespread cloud, and where the model, due to the resolution to this fishing net, can represent, because there are lots of points in this net that falls in that cloud swarms. Now, if you go to the green one shows very small white dots, and these small white dots are so small that they fall between the grid scale of this fishing net. And this is what we call unresolved scale. So we have to take them into account, but it's like, when we use a fishing net and the small fish are passing through, and we cannot uh, capture these fish because they are too small, but they are living in the water, they are there, but they are very small. So we cannot, let's say, the models are able to represent better the larger scales, as we saw in this example of a frontal system that is represented inside of this red circle, compare with the small scale cumulus that you see by that tiny white dots that are enclosed in the red, in the green circle. So it's we have to be aware of this limitation of the models. But I have to say that currently this horizontal grid resolution in the global models is around 10 kilometers. So it's much smaller, much finer than the resolution I show to illustrate the example. And because this resolution of the fishing net is very important, I wanted to share with you a nice example of representing a hurricane that you can see on the right side panel. So this was Katrina some years ago, so in 2005. So this is Gulf of Mexico. So in the north you have Texas, New Orleans, and so on. Texas on your left. And you see the eye of the hurricane. So this is a satellite picture taken on that day. And we know that this had a very severe impact in New Orleans. Lots of people died, the infrastructure was badly affected, and so on. So if now I will show a sequence of model forecasts, each one has a different resolution, and we will try to see how the model sees this system that occurred. Okay, so the model is trying to simulate this system, and we will try to understand how the resolution, so this grid size of this fishing net is important. So the first one was a model version of 1979, which has this grid scale of 200 kilometers, and you can see the size of the grid mesh is this kind of pixels that you see. And looking to that, you will not recognize at all a tropical cyclone. You could see some whitish pixels, but nothing that will give us a hint of a tropical cyclone. Now, the version of the model in 1985, which was basically half the resolution, also you could see a kind of a white blob in the middle of this panel, but nothing again that would say that was a tropical cyclone or a hurricane. Again, 1991, we reduced, so we started to have a finer mesh, but still we see at the center more brightish colors, but nothing that again would say is a tropical cyclone. And then if we go on, once we get finer and finer resolution, then we start to see, in fact, the model resolving this system. And in 2006, we can see already the eye at the center of the tropicals of the hurricane here, as we saw in the observations. And let's say the version of the model in 2010 with 16 kilometers of fine scale can immediately pick up the main features of a tropical cyclone with the eye resolves the eye wall of a tropical cyclone. So it is something that is important in order for us to get the small scale resolutions like a sea breeze or a wind gust. It's important to have very high resolution models. Okay, but we have a problem, and one of the main criticisms that I received in my professional life is why the forecasts are always wrong, or that has been the main criticism of the people every time I speak with them. So, and we have this nice citation of Edward Lorenz, which was a genius and important scientist that contributed a lot to atmospheric science. And he has this nice sentence, which I think probably you already have heard somewhere, that does the flap of a butterfly wings in Brazil set off a tornado in Texas. So he wanted, of course, this is a metaphor, and he wanted to illustrate with this metaphor that we are dealing with a very complex, non-linear system, which, small errors in the initial conditions and the model that we have nowadays can produce or can generate or amplify errors which propagates, let's say, in the next days, and of course make a bad forecast. Okay, and one way to circumvent that problem is to use, instead of a single forecast, to use a set of forecasts. So we try, instead of generating a single forecast, we generated an ensemble of forecasts, which provides a kind of different trajectories, as you can see by this example. So imagine that the circle on your left side is the initial condition, so the starting point, and of course each start line that you see here in blue is not starting from the same location. They are separate a little bit apart, and once we started, so these small differences is the uncertainty of the initial conditions, because as I showed to you before, we have quite a lot of observations over Europe, but over Africa we have very few observations, especially over deserts. And and because we have only very few of them, we don't know what is the state of the atmosphere on a specific location in the desert, because we don't have observations. So there are some uncertainties. We try to make a guess, a best estimate, but it's always very difficult to determine. So once you start the forecast, you have these individual lines that will show different outputs. And in this case, you can see by these little squares is the rain showed by these shaded green colors is the rainfall over UK at a specific time in the future. So, and you see that each frame is different from the other, which basically shows the uncertainty of the forecast. So instead of saying it's a, uh, it will rain in Datchet in 3 days' time, yes or no, what will be the probability of raining in Datchet in 2 days or 3? And then we provide a probability of chance, so the likelihood. Okay, so it's the best approach to make a forecast. And this is another example. So I took this from yesterday. This is what we call the meteogram. So the meteogram, you see these boxes, these CM boxes, and the boxes are more elongated than others, so at the beginning of the forecast. So what you see here is the time is on the horizontal axis. So we started from yesterday, Tuesday, 7th of April, and we will finish on the 17th of April. Okay, so this is our time, and this is basically on the bottom you have the temperature, on the middle panel you have the wind speed, and on the top we have the rainfall. And this basically the more compressed boxes or the elongated boxes will give us more certainty or uncertainty of the forecast for the weather that we want to make, okay, or to understand what will happen in the next days. So let's make an exercise, for instance. So this box plot, as you see from on the right side, represents the probability. So at one point, these small segments in the box plot represents basically the probability. So 10% is the bottom horizontal line, the wider one represents 25, then we have the 50%, 75, and 90%. And then we have the whiskers, which represents the maximum, the absolute maximum of precipitation or wind intensity, and the minimum, which is the whisker pointing to the bottom, okay? So this is the way for us to quantify the uncertainty for some weather parameters, okay? And let's make an exercise. Let's suppose that we want to see what will be the strength of the winds for Datchet for the bank holiday, okay? If we make, let's say, if we look here to, let's say, 40 knots, which is around 7 meters per second, and if we look to the end of the arrow, we see that we have around 70% probability that we'll have winds that will blow up, let's say, up to force 4, okay? But if you let's say want to assess the risk that for some possibility the winds will blow, let's say, more than that, I would say let's look here to 23 knots, which is around force 6. You see that we have a very small percentage, so something that is pointing here on the red circle, so less than 10% chance that winds will blow quite strongly in Datchet. Could be approached in this way, saying is it will blow force 4 or not, a kind of a binary answer, yes or no. I think that is not the right way to look into the weather forecast. And of course, you have other products, if you decided to go with your dinghy in the open waters in the ocean, you can also look to the probability of having a significant wave height above 4 meters. So this is a way for us to provide information not only to the public, but also to the specific users, like the people responsible for races, you know, or ship routing or whatever, are basically the main users of this kind of information. And finally, just to say that the Met Office, which is the official, basically, institution of UK to make basically public weather warnings, has integrated this approach. So this probabilistic approach, this chance, this likelihood of having some severe weathers. And this is a kind of way that they found to basically pass the information to the general public, where you have this warning impact matrix, where on the vertical axis here you have the chance, so unlikely up to very likely, the chance of any kind of phenomena. Could be, you know, snow, could be waves, could be heavy rain, and so on. So there is a chance of likelihood of specific events and the impact of these events, because if you are in a very dense populated area, of course the impact will be much higher of heavy rainfall with disruption for travel and so on, than if you are in a very in a low dense population area. So these are ways to transmit, to tell to the public and play with the chances, because it's the best way, in fact, to make this approach of weather forecasting. So just to summarize, numerical weather prediction requires what? Advances in science. We need to know, we need to understand better the processes that characterize the atmosphere, the oceans, and all the interactions between the different components of the planet Earth. And also we need international cooperation, because one country per se cannot do this huge effort, which is basically screening the global, on a global scale, the atmosphere. And of course, the progress in computational technology. So computers here are very important. They in fact, they compensate the thousands of workers that Louis Richardson imagined 100 years ago. So finally, the last slide is just the quiz that I tried to show at the beginning. Is this, which one is the real one? The left one or the right one? And thank you very much. Fiona?
Thank you.
Thank you. That was amazing.
Well done, Fernando.
Sorry
Well
to
done.
take more.
That was fabulous.
So, any questions? I don't know.
Well, the only question I've got is, obviously your forecasting doesn't allow for Wales, because as we all know, it always rains in Wales.
Exactly. I don't say anything, you know. It's what I can, but yeah. So yeah, it's a very complex. So it's a state of the art. It's science, and it's a huge logistics behind to provide what we see at the end, which is these nice apps with nice graphics showing the winds and so on.
Yes.
Also dances in statistical mathematics as well as science.
The physics and the maths and the probabilities. And at the end of it, questions. First question, you haven't allowed for Wales, the country, because everybody knows it always rains in Wales.
My friend. Actually, it doesn't, but yeah.
I have a question, Fernando.
Yes.
So when I'm looking at my forecast ready for the racing,
Yes.
there are many different models to choose from, and
Yes.
exactly as you've just described, they've got different grid sizes, some down to you know, just a couple of kilometers. Is there
Yes.
a trade-off, or no, I'm sure there is. What is the trade-off between the grid size and the reliability or the probability of the forecast accuracy?
In theory, let's say the finer the mesh, the more reliable is will be the model or the forecast. Okay, in theory. So it's not a straightforward answer, but I'd say most of it, if you have a more, let's say, a high resolution model, you know, let's say 1 kilometer model against 10 kilometer model, a 10 kilometer resolution model, I would say the 1 kilometer is more reliable. Okay, so why? Because as I showed that in one of the slides, so the weather parameters will be distributed on these nodes of the grid. Okay, and when the model computes that value, let's say the wind field or the wind speed or wind direction, this is a value average over that grid cell. Okay, so if you have, let's say, 1 kilometer is different from a 10 kilometer. Okay, so we have to take into account these considerations. So the parameters, the weather parameters, are computed for or are the result of an average of the grid cell. Okay, of course, then you can elaborate a bit more, and you can combine a kind of a post-processing techniques in order to give more point-wise values. Okay, but this is, let's say, downstream of the numerical weather prediction. I don't know if I answered to your question, Simon.
You did. But if you get if the mesh is too small, and using that 1 kilometer versus a 10 kilometer example, does it not sometimes increase the probability you're just exactly wrong because it's trying to be too precise? So, for example, Datchet is more or less a kilometer grid, and if a relatively small rain cloud comes across and it comes over Heathrow instead of over Datchet, there's only 1 kilometer wrong.
Yes, yeah.
It's sunny in Datchet, but the forecast says it's going to be raining. So,
yeah,
whereas if it was a 10 kilometer grid, you have a
yes.
average.
So, yeah, you use two concepts which they are not directly related, because you said at one point you use the concept of probabilities and finer mesh. Okay, so probability, because as you said, because if you have a front that for some reasons goes through Heathrow and miss Datchet, okay, what the best approach for that is to have an ensemble of weather forecasts, okay, which will try to measure the uncertainty if the front will, let's say, pass over Heathrow and not reach Datchet, or the other way around. Okay, so the concept of probabilities is to overcome the uncertainty of having these situations where you may say small scale structures like a shower, an isolated shower, can affect Datchet, but can not affect Heathrow Airport. Okay.
Yeah, clear. Thank you.
Fernando, I
Yes.
take it if you want to increase the resolution of the grid, then you need to increase the data points being entered into
Yes.
the mathematical model.
Exactly.
Okay. A related question is, if you double the resolution of the grid, what's the increase in computing power required to interpret the models?
Look, it's quite a high number. I don't have, to be honest, I don't have in my mind what are the increase in terms of computational, let's say, computational in terms of floating points per second. What I can say that we are facing nowadays with big challenges because we want to increase the resolution. As I said, this resolution of the grid is very important, and we want in the next 10 years to increase the resolution of these models, the global models. So imagine on a global scale to have values of temperature or wind speed every kilometer apart. And for that, we need big computer power, okay? And in fact, this will be an obstacle if we don't have enough computer power in order to provide this forecast at one grid resolution, okay? But it's a challenge, eh? It's a big challenge for the near future.
Is there any?
I was going to say, can I throw in a point? And that is that I think. Hello, can you hear me? Yeah.
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 Yeah, can I throw in a point that this forecasting is not necessarily ground level, because we get forecasting of your level is probably what I would refer as my piloting days as a 2,000 foot forecast, because then you have the microclimate image underneath, which will affect a lot of things. For instance, at Datchet, we certainly get a lot of changes due to the airport. And I have flown and sailed in little bays and places where you can actually forecast what is going to happen, because you're in the stonking great high and it's all just thermal. And so as sailors, especially dinghy sailors, we mustn't get too fixed on what a forecast is from these big global pictures, because while they're incredibly useful, the local conditions also will affect it. Would you agree with that?
Yeah. So first point, when I show this this example of a grid mesh, and I show basically involving the globe, I didn't tell the full story, because the current models, I can tell you, the current models, they have several levels. So they have 137 levels that goes from the surface, near surface, up to 80 kilometers high. Okay, so imagine a 3D grid, okay, which goes from the bottom, so close to the ground, up to 80 kilometers. So, and each point in the vertical, you have 137 values of temperature, humidity, wind, pressure, whatever, okay? So it's a 3D model, okay? So it's not just 1D, let's say, or 2D model in this case, okay? So that is the first answer. The second is, while in my working environment, we developed a global model, and this is our main responsibility, which is to produce global forecasts. So provide the evolution of temperature, humidity, wind, and so on a global scale. This data then is used by the Met Office to generate forecasts on a regional level. So they have what we call the limited area models, so regional models which basically cover the entire UK with a resolution of 1.5 kilometers. Okay, so but to produce that forecast on a very fine scale, they need the information on a much wider scale, which is provided by us. So it's global to regional. So in regional limited air models, they can provide detailed information for the next 3-4 days with a resolution of 1.5 kilometers, something around that value, every so in each grid point. Okay, so that, and of course with that resolution you can include, you know, the hills, you know, considerable, and probably big lakes, you know, at least with higher size than 1.5 kilometers. That is all also included in those models. So that is basically what the Met Office tries to do to complement what we provide to the member states, which the Met Office is one of the members.
So, quick question, Fernando. Do the models take into account the surface construction, whether it's concrete, whether it's grass, whether it's
yeah.
Yeah.
So, but let's put it this way. So, what, as I said, for the global models, or let's put it this way, for the Met Office fine resolution model, which has 1 kilometer or 1.5 kilometer, we use, so basically it's a kind of a grid of 1 kilometer by 1 kilometer, something like that, okay? And they have to provide information in terms of a tile, you know, what kind of tile that represents the ground at that location, you know. I would assume that if there is a tile that encloses the Datchet reservoir, he will take into account not only the fraction of water that is enclosed, that grid size enclosed the Datchet, but also, you know, tile information about, let's say, the type of vegetation or the fraction of building, density building in that. So everything is combined together and telling to the, basically to the equations that the fluxes between the ground and the atmosphere has to take into account having a body of water, a type of vegetation, and so on. So I don't know if I answered to your question.
You did, yeah.
Yeah. Okay. So it's very complex. I have to say it's very complex nowadays. Models, which tries to take into account all these aspects of, in terms of characteristics of the ground. Okay, but of course we are still far from very fine resolution, you know, to be able to distinguish the Datchet sailing club or the building, even the building, you know, which can constrain the winds when they are blowing and see the building, they move around. So those, in that future, that probably will not be my future to see that, but will be probably models which has a resolution of 10 meters or whatever.
Wow.
So it will be interesting to see those days where they will provide very complex and sophisticated information in terms of representing the winds.
Is the limiting factor in that the computing power?
No.
Yes. Yes.
Yeah.
Definitely. Definitely.
Yeah. And I was interested in quantum computers. I went to a seminar on that last year, and that feels like it's something that will be quite useful in meteorology because it sort of suits that style of processing. How far away do you think that might be before we get that being used?
Sorry, I cannot hear quite well because I can hear you on and off.
Okay.
But I think you were referring referring to the computer power. Look, we cannot move on. In fact, if we don't increase the computer power to represent this kind of details in terms of weather prediction. So unless there is a kind of a revolution in terms of computer power, in fact, we will not be able to achieve that.
So could that be quantum computers?
No.
Quantum computer?
Yes, exactly. Yeah, exactly. The quantum computing that started, I think there was a first experiment using that concept, which I don't know exactly what can be, but apparently could be the next step in terms of computing power that we need, in fact, to get that kind of detail in the future.
quantum computing used back in 1990 was used to pull in everybody's individual PCs if they signed up to it, to allow processing power to be involved in the analysis of the human genome.
Yeah.
Which worked well. It worked well, but it was everybody else. What I would suggest is that the only way you're going to improve from what you're doing now is another input, which would be visual interpretation. So there'll probably be some sort of video interpretation, picking out high buildings, low buildings, and that might help.
Yes, yeah, but that has to incorporate it in the model. So the model has to identify, you know, how tall are the buildings, you know.
Indeed.
Let's give a very simple example. You know, we know that high dense population areas like London, the Great London, they represent a kind of a what we call urban eating island, you know, because of the number of density of houses, traffic, and so on. And it's difficult. For instance, even nowadays, the global models, they cannot represent these urban islands, let's say, because we don't take into account the human activity there. So whenever we generate a forecast, a temperature forecast, probably for London in general, we are doing some systematic errors because we don't take into account these urban islands, especially for the situations of let's say very cold days in winter. You know, so we may be off a few degrees in terms of temperature because we don't represent this urban heat islands as we should do it in reality.
Fernando, at a more general level, Met Office makes all these predictions. Do all the other broadcasters, BBC and others, are all their forecasts based on the Met Office information, or are they making their own predictions?
Okay, so as you know, BBC, I think a couple of years ago, they lost the contract with the BBC, which was a very long contract for dozens of years, to a private company, the Meteo Group. So the Meteo Group is a kind of is a private company, basically. I think is somewhere the main companies, I think, in the continent. But basically they use many models. Okay, so they use our model, but also they combine our model with the Met Office model and whatever Met Office produce, because Met Office also has a global model and also these regional models, as I explained before. So they use a huge amount of information, and then the forecasters, so the people which looks to these values, they twist a bit accordingly with their own experience and with some more complex algorithms to process this information. But I have to say one thing, because it's a private company doing a public forecast, but we should not forget that in terms of severe warnings, the official entity is the Met Office. So the Met Office is the only institution in the UK which is recognized to issue severe weather warnings. So the guys in the BBC, which are owned by this private company, they have to be in line with the Met Office every time they have a severe weather. So the main guidance in terms of severe weather is provided by the Met Office.
Okay, thank you.
So they cannot, let's say, just to finish, they cannot predict something in terms of severe weather in the BBC, which is contradicting the official weather warning that the BBC basically disseminate to the public in general. Okay?
Thank you.
Yes.
Amazing. Does anyone else have any other questions?
No.
No?
One last question. Is there any use of machine learning in the calculations in the model?
Okay, that's a good question. You know, over the last 2 years, we have been boiling in our institution, and not only in our institution. The Met Office is doing the same thing, which is trying to understand where the machine learning could be important to be to be used in developing further this model. So it's still something that we know that is very important. We don't know exactly which areas in this infrastructure that will be fundamental to improve with machine learning, but it's something that we are now considering heavily to use them in the future, definitely.
Yeah, I was wondering whether it could be used for identifying patterns that may not be apparent to human analysts.
Yeah, definitely.
Well, Fernando, I just wanted to point out that some 30 years ago, I studied meteorology as part of my pilot's license.
Yes.
And at that time, I was told that unfortunately it was all going to get very, very, very much worse than it was, due to the fact that the Americans had sold the world on weather satellites, and all the base stations were being decommissioned.
Yeah.
So all this local data was disappearing. Now, I'm really pleased to see that you still have loads of local data, and that in fact the satellites have improved dramatically as well, because certainly the forecasts of the last 3-4 years has been so much better from my point of view as a pilot that I just wish I was still flying, really. But unfortunately, Gabrielle sold me a boat.
Yes, exactly. No, but
done,
it's interesting
Gabrielle.
that point. It's interesting that point that you mentioned about the possibility to discontinuing the observation, the conventional observations.
Yeah.
As once we started to have a lot of satellite. But don't forget one thing, that in order, the satellites, they measure radiation, okay? And you have a very deep atmosphere. So they want to, what they measure is what is coming out of the top of the atmosphere, okay?
Yeah.
And of course, this is backscattered. So there is a lot of processes going on. But in order to calibrate those sensors, to understand exactly what they are measuring, we need, let's say, the other data, the conventional data.
Absolutely.
These balloons that make profiles along the depth of the atmosphere. So without that, we were a bit blind to try to understand exactly what those values were measuring in the sensor, in the satellite picture. So we need both of them in order to, understand the measurements and to calibrate this.
Yeah, I was going to say that the fact that the aircraft now report back is obviously reverse of that trend back then.
Yes, exactly. But it's interesting, over the last weeks in the community, in the observation community, because there are lots of technical people and responsible people to launch these observations. Once they realized that the number of drops provided by the aviation was going dramatically down, they decided to increase the frequency of these balloons, the radio songs. So in a way to compensate the lack of observations or the reduction of observations. So this is a system that tries to compensate each other in order to keep the level of quality of observations in density and quality in order to feed up the models. Okay, so it's a compensation, but only with coordination, which is not possible on a regional or on a national level. You need a lot of coordination cross boundaries because it's a huge effort.
Well, Met is a global thing.
Yes, exactly. Okay, so Fiona.
I think a massive thank you to you, Fernando. That was
Absolutely.
fantastic.
Thank you, Fernando.
Sorry for my bad English. for my
Oh,
presentation.
it was incredible. No, thank you so much.
I hope you could get a clear picture of what is behind the numerical adaptation.
Yeah, that was fascinating. So thank you so much for delivering us that presentation, and I'm just so glad that we've managed to do it.
Yes.
Obviously not as the original plan in the clubhouse, but that we're all here.
Exactly.
And we still managed to hear that amazing talk. So thank you so much.
No, thank you very much, Fiona, to set up all this thing. Without you, probably it was impossible. So thank you very much for your time and effort. Okay.
And hopefully we can run some other different activities on a Wednesday in the evening while we are homebound. So Gabrielle mentioned at the start that we are trying to put together a little talent show. So if anyone has any talents, we're going to try and put it together, and so we can all watch it one evening and
I'm quite good at hiding.
Provide some entertainment for everybody. So yeah, if you do have any talents, or they really don't have to be talents, just anything that's going to be, you know, kind of entertaining or informative to people, put something together, and that would be amazing. You could, you know, read us a poem, do a monologue.
Yeah, monologues. I'm pretty good at monologues.
Can you play that machine behind you, David?
Ooh.
David, can you play that musical instrument behind you?
I used to be able to.
The bedpan.
There you go. That we're expecting a video of that. I'm telling you.
Okay. Yeah, I can hug it.
And Helen, we're expecting your party piece.
What's that?
Oh, Helen's got an amazing trick with a pair of tights and some. I can't remember what it was. Was it bottles?
For family viewing?
Listen, it's our talent show.
What
and Tony, are you in? Are you in, Tony, with a bit of quality?
I don't know about the quality.
Never mind the quality, feel the width.
You'll give it a go, Tony, will you?
I might even have a camera working by then.
Excellent.
Which would be a bit better if I'm going to do a monologue.
Well, that's your challenge, and we need it in quite soon.
When do you want to do this?
And we'd like to do it next Wednesday night.
That sounds fun.
Well, how long does it take you to play, David? Have you got to learn?
I could always send you a picture of my saxophone.
Oh, play it. That's marvellous.
Yeah, perfect.
I didn't say I could play it. I just said I can send you a picture of it.
Give it a go. Give it a go.
You could get some music of someone else playing it and just convince us that you are.
Mime.
Especially why I haven't got a camera. That's not a bad idea.
And Alistair, we'd really like to see some virtual surfing there.
Oh, I haven't got. Actually, I have got a surfboard here.
Yeah, perfect.
There you go.
Or a windsurf.
That'd be great. And if anybody knows any other member that has got some, you know, hidden talents, can we please get them to do it?
Yes.
It'd be great. And I don't know if anybody hasn't done the virtual regatta on Sundays, it really is worth a try.
I'm usually too drunk on a Sunday.
And if you need any help setting it up, just let me know and we'll talk through it.
Yes, it's been good fun, hasn't it? And
it's been great
24
fun.
On the line, so good way to sail. Has Fernando gone? Where's Fernando?
Yeah, he said he's just ducked out. He's really hungry.
Okay. Well done. Yeah, I think that was great. Thank you.
What happened to Keith and his curries?
I know.
Even my pub does take away curries.
Right, we'll tell Keith.
I love the resourcefulness of the businesses. Our local brewery does deliveries now.
Oh, really?
Yeah, yeah. One of our local breweries is doing deliveries. Small tubs.
Testing wine are doing deliveries apparently. But of course, off license are essential services.
Absolutely. So it's going to Tool Station for a piece of what was it? I got this afternoon. Oh, flash bend. Yeah. I'm trying to work my way up, going to the pub, going up to the supermarket for some beer, but I've not managed it yet.
Hey, David Fulcher. Sorry.
I think the government, my theory is the government need us to keep drinking so we stay calmer.
That's good. I can
That's
work
why
on
they're
that.
essential services.
Yep. I can work. Psychological support.
Yes, indeed.
I'm really sorry, but I've just seen David Fulcher. David Fulcher, we're waiting for your party piece to come in for Datchet's Got Talent. I know you are good. So
you could do a Two Ronnie sketch.
I'm expecting a video from you.
So Gabrielle, what's your party piece?
Don't.
Yeah, I'm doing it right now.
Sitting in the dark.
I'll pull it together. Right.
I'm going to go, guys.
Yeah, okay.
Yeah,
Fabulous evening.
Thank you so much, everybody, for coming out. It's lovely to see you all.
Yeah, that was good.
We'll try and keep this going.
Yeah, why not?
Organising it.
It's the first time I've ever used Zoom. The first time I've done a video thing, actually, or even though it's not video, but I'll work that out.
Well, we can have another test run at some point. If you want to give it a try, change some things and see if we can get it running, we'll have a test go at some point. Just let me know.
I'm slightly nervous because you'll have seen how many glasses of wine I've got through during the evening. But... Yep, we'll give it a go.
Okay, perfect.
Thank you very much.
All right, thank you, everybody.
While you're out running or walking.
Okay, bye.
Good night. Bye.
Bye.
Bye. Bye. Bye.